Doesn't look like that on my screen. Looks like that. Okay. I'm going to talk a little bit today about piezoelectric MEMS and thin films and structures that really cross length scales. We're using some nano components, coupling with some micro components to make some meso components to hopefully provide a decent amount of electrical power from some scavenging kind of systems. But today I'll primarily focus on, if I can learn how to do this, piezoelectrics and thin films. I'm Dave Bahr. A lot of this is actually done by Dylan Morris, who's a postdoc with me, who's leaving next week to go off to NIST, and I got a bunch of money, a bunch of different folks. And of course, I don't actually do anything anymore. It really is primarily Dylan, Molly, Michelle, Julia, Ben, Adam, and Phil, along with my collaborators Bob Richards and Sil Richards in mechanical materials engineering at WSU. So we got started looking at ways of trying to harvest mechanical power, or harvest electrical power from surrounding ambient conditions. Obviously, there are a lot of groups that look at this. There's a lot of ways to do it: thermal, vibration, chemical, solar. Thermal and vibration are what I'll concentrate on today. And in thermal, we were particularly interested in waste heat applications. The low-grade heat mentioned this morning that we throw away a lot of places. And so we're not going to necessarily have things that are extremely efficient, but if we're throwing it away anyways, maybe if we can make it economically and make enough of it, it'll be worth scavenging. Vibration is particularly attractive for aircraft systems, for unattended or for sensors and wireless sensing networks. And we want to know, can we make an efficient power supply for remote sensing? So what we've been playing around with for the better part of 6 or 7 years is what we like to call the P3 micro power generation system. P3 is Palouse Piezoelectric. WSU is up on an area in eastern Washington which has 1, no trees, and 2, rolling hills we call the Palouse, and so therefore, what the heck, seemed reasonable. We were going to do MP3, but apparently that was already taken. So what we do is we have a cavity that's filled with two-phase fluid, liquid and its vapor. We apply heat through a thermal switch that causes that fluid to expand, or the fluid to evaporate, pressurize the cavity. The cavity has a piezoelectric membrane. We're going to strain that membrane, generate charge on the membrane, take the charge off, cool the cavity, repeat over and over. And some of what we've been doing in terms of how we structure these materials is looking at thermal switches that can transfer heat in and out of the cavity as we flex the membrane from a hot side to a cold side. The thermal switches we made, about the best we can do right now is about 3,000 C per second in terms of rates, which is pretty good, using mercury or gallium droplets. Of course, because we had to, we made nanotubes, because people give us money to do that, where the nanotube structures are vertically aligned carbon nanotubes. These things might be on the order of 20 to 30 microns tall. And since we have trouble sometimes, we coat them with gold to make better contact. And that tends to be almost half as good as a mercury droplet switch or gallium droplet switch. But the idea is that we have a modular system where if we heat up this fluid and we can pass the waste heat from one into the next layer on top of it, we have a little set of engines that we can lay out in sheets or stacks, take advantage of different low-grade heat, and hopefully be able to hit efficiencies on the order of 1 to about 8% of Carnot efficiency. So we do this with our little piezoelectric generator. We apply heat at 40 hertz. We have the thing oscillate. You see a mechanical output. And typically we operate at pressure somewhere between 5 and 25 kPa. So we have these little millimeter across, micron thick, with nanostructured bits underneath, moving heat in and out, heating, cooling, generating electrical power. So it's a tiny little external combustion engine.
So what's the fluid in there?
The fluid we use right now is Fluorinert or PF5060, depending on which student's doing which experiment.
So with sort of a third of a bar on it, you hardly change its phase transition temperature at all.
We in fact don't want to change the temperature. We keep it at its vapor pressure.
That's bad for Carnot cycles because it means that delta T is 0 for the guts of the engine are very small.
Right. We've actually designed this to work over about an 8 degree C delta T.
And that's the change in...
That's the change in delta T.
And is that also the change in phase transition pressure as well? You know, the car is not a problem, right?
Right.
If I have a latent heat for this phase transition, if it all occurs at the same temperature, then delta T is effectively zero.
Exactly. And we don't get, let me show, when we do our hot and cold switching, we're actually switching around 15 to 20 degrees C, and we try to get small delta T's. We're trying to scavenge some low-grade heat, dump to ambient instead of cold temperatures.
So you eat sort of half or three-quarters of the delta T of thermal conduction.
Yeah. So, what I'd like to spend the rest of the time talking about is then, once we get a little bubble that's straining a membrane, it's a piezoelectric membrane, we want to take some charge off it. And when we started doing this, there are a lot of folks that make similar structures where we have a piezoelectric structure on a support membrane, silicon, oxygen, some other stuff. We use PZT as our favorite piezoelectric. It just happens to be our favorite. We can pick some other things that work at different temperatures and different conditions, but for our purposes it works out pretty good. And what we started with was looking at how do we get more energy, or how do we get an efficient coupling conversion between mechanical to electrical energy in a piezoelectric film. So the way we started testing this was just make little piezoelectric membranes, and I'm silly and I'm not that smart, so I just pressurize them. We bulge test them out and measure displacements and pressures and get a pressure deflection relationship. And if we do that, we can calculate a residual stress in the films. And because we're actually trying to make these things relatively large wafer scale devices, we end up with relatively high tensile stresses because I'm cheap and we tend to use thermal processing that's a little too high at temperature, and you end up with tensile stresses in the film. But we can calculate all of that if we measure the pressure deflection relationship on one of these little membranes. So then we wanted to look at what's the efficiency of an oscillating piezoelectric membrane that we're forcing. So we'd like to force this at the resonant frequency of the cavity which has the fluid and vapor in it. So the first thing I'll point out is that the numbers I use for Q, I'm not missing a K or an M. I'm going to use numbers like 20. Not 20,000, not 20 meg, just 20. It's because this cavity has a bunch of fluid. We have a lot of dissipative mechanisms within the cavity that will hurt our Q in the device. But we have K squared, the piezoelectric electromechanical coupling, and Q, the resonant, the Q of the engine itself. And we can test these things in a vacuum or something, measure relatively high resonant frequencies, and measure relatively good Qs. Later on, we'll be testing them with a bunch of fluid behind it, which will drop all of that frequency down somewhere around here and make the Q look something like this.
What's the thickness of the gas layer?
The thickness of the gas layer or the cavity itself?
In the gas layer in the cavity.
The total cavity thickness is on the order of about 40 microns. We vary between 25 and 50. We use a wicking structure to bring in fluid, so the fluid's about 1 micron thick. When we evaporate it, then it evaporates, has a hot side, and the cold side recondenses up on top.
So the thermal penetration depth is much bigger than the thickness of the cavity.
Yeah.
So you're in the isothermal unit.
So, piezoelectric cavities, we have an equivalent circuit model that'll let us back out things like coupling coefficient Q. And so for the way we assemble these in an engine, our old DARPA program manager used to do MEMS and say, well, we'd be out here somewhere. Well, unfortunately, with all that fluid back there, we're somewhere around here. So what becomes important is the electromechanical coupling coefficient of the device. Our Q is not going to vary much between about 20 and 50. And so we're stuck trying to make higher K squared values rather than push our Q values up. And the overall efficiency of a resonating cavity at that sort of structure, if we end up with something like a Q of 1%, well, we're going to be about 10% efficient for mechanical to electrical. And for most of the materials we're using, we actually have a K squared somewhere around 5 to 10%. And so that should put us up kind of in the 30 to 40 mechanical to electrical conversion. So the first problem was we went ahead and made these and started testing them, and they were, what I'm looking for is abysmal. And so we had, of course, that gives us more funding to look at why they were so bad. And they were bad because we had a relatively high residual stress. We were pushing on a drum that we tensioned. So we had to think, well, what could we do to beat that? Well, we worked out some modeling, and we should have our k-squared values increase as we decrease our residual stresses. So the residual stress in a piezoelectric membrane structure, kind of like we were making, is somewhere around 100 MPa, and the boundary conditions should make a difference once we're at low stresses, but at high stresses, they don't matter. So we thought, okay, if we just lower our residual stress, we will see an increase in our k-squared, and our devices will get better. That would be nice. So, of course, we had to balance our residual stresses. So we went from having something that looked like that to saying, instead of using a silicon support structure, we'll use a silicon oxide support structure, grow the oxide so it's compressive. We can do that, and while it makes pretty pictures, this is a really hard device to handle. I like the wrinkling, but we're not quite sure how to package that. So we then backed up and said, well, let's stay just barely slightly tensile. And we did that by sticking this compressive oxide. There's our ti-platinum electrode, which is tensile, and the PZT, which is the biggest tensile component. So the overall membrane now, or diaphragm, has a stress of about 10 MPa instead of what we started with at about 100 MPa, which should give us something like an order of magnitude increase in our k-squared. The one other way to relieve some stress would be to go ahead and corrugate the structure so that we had a piezoelectric membrane here and had some corrugations that could relieve the stress during thermal processing, and just pattern it, wet etch it, because I'm, again, inexpensive. My wife says I'm cheap, but I'm inexpensive, and we end up with a corrugated structure. And so we can now have a corrugated piezoelectric structure, a low stress structure, or the original high stress structure. We can measure pressure deflection relationship, and we find out that our corrugated structures give us, we did this in log scale because otherwise you don't see much, you just see the corrugated being much, much further out. And what we end up doing is a couple things. The first thing is that we shift the behavior to cubic from linear to lower pressures. So at a lower pressure, because we're doing a heat engine, we're actually in a pressure limited case. We're not in a strain limited case. We can only generate so much pressure on any given heat pulse, and so we want to get to a point where we get a large deflection and for a small amount of pressure. So corrugating it helps us do that. We measure k-squared, something around 1,300 times 10 to the minus 6, which is still not that good. And the Qs in the corrugated structures were around 40, about 20 here, and about 1,400 ppm. Anyways, overall efficiencies on these things are somewhere around 1 to 2.5%. So that made us look a little bit harder at how we actually have to work with one of these membranes. We can drive these at relatively decent frequencies and relatively good amounts of power. We get somewhere in the neighborhood of about 400 microwatts coming out of a 3 millimeter lateral dimensions vibrating structure. So they do output enough power to run small electronic signals and devices and sensors, and couple in with some RF electronics for sensing and signaling back to your home base for accelerometers and such. So we had our k-squareds, and they're still not what we'd like them to be. We'd still like them to be much, much higher, and so we started looking at this a little bit more carefully. And for the PZT we use, or we use, the best we're going to get on something like a k-squared is about 5 to 6%. And that's really based on a couple things. First off, and we're not the first people to point this out, there are quite a few people. Paul Morrell used a figure of merit to define efficiency and power generation, which was piezoelectric constant squared divided by dielectric constant. We threw in modules just to make it a little bit easier for us to work with. And so we see we have our piezoelectric coefficient, our dielectric coefficient. We can change these properties through doping and some other things about processing. That's a lot harder to change, so we're not going to change it. We said, okay, well, that's as good as we can get for a stretching membrane. But then came up the question that a lot of times when you work with small membranes and small structures, you make small oscillations and deflections. But our device doesn't work using small oscillations and deflections. We push the bejesus out of it. We pressurize at 25 kPa, and we'll take one of these 3 micron thick membranes, 3 millimeters across, and do an out of plane displacement of about 150 microns. So we're not bending it anymore. It doesn't look like this. Effectively, if we were bending the device, which which is what we do for this kind of plot, the device has to have this kind of shape. But we actually pressurize it out so that the deflection goes as low to the 1/3 in this case. We have negligible bending stiffness, and basically we have a large in-plane stress. And so it led us to think, well, maybe we're looking at this wrong. Maybe we shouldn't model things like this. Maybe we should model as pushing out on balloons instead of pushing out on plates. And we go back and read things about people doing small plates as MEMS, straightening out to large displacements, and Begley's group in particular put a nice way to do it. That if you had residual stresses and residual strains, you could calculate, should you treat something as a plate or a membrane, depending on what these various parameters of stress and strain came out to be. And you can map out something like how much you're pressurizing the membrane on the back versus how much it's pre-strained. What you find out is that for every one of our cases where we actually operate the membrane to generate somewhere in the order of hundreds of microwatts, we actually come down here into a nonlinear membrane as opposed to our original plate model. And if we increase the pressure, we do go this way. But very often what we're doing is we have a little bit of a residual stress, and we stay kind of near this nonlinear membrane region. So if we have a nonlinear membrane, let's look at what happened was it was behaving similarly between a simply supporting clamped piezoelectric membrane because it's already behaving like a membrane. So let's work out how we should do piezoelectric coupling for large displacements of piezoelectric membranes for power generation. By the way, this also works for sensing and actuating, but we'll think about it for power generation. So if we strain a membrane to a large displacement, and then we put on a small oscillation either in electrically or mechanically, and I'll show you both situations, then measure the resulting displacement and the pressure deflection curve, we should be able to back out what the coupling coefficient is in this system. So of course we do that. We have a small little piezoelectric membrane, stick some probes, start it oscillating. And we find out that first off, as we pressurize the membrane, we can either push it outward or downward. So we can either pressurize back and forth. And when the membrane actually works for power generation, it oscillates somewhere around 0.
So under there?
This is all under there. Actually, I'll do a couple sets. This is air. We do it with the fluid behind it, and that'll just drop the Q's a lot and drop resonant frequencies because there's a large effective mass, and it acts as a squeeze film as the fluid evaporates and wicks down a wicking structure that brings the fluid from a reservoir into a thin, hot area. But yes, this is it. So we can pressurize the membrane back and forth. We get changes in frequency response. That's nice. And so what we do is we say, well, we have a linear component in pressure deflection and we have a cubic component. The linear term is going to be solely related to the residual stress, and the cubic term will be related to the modulus. And so we should be able to change the effective stress by changing the charge on the membrane. So what we do is we go ahead and we can test an open circuit or closed circuit. And if we apply a positive bias to the membrane, it looks stiffer than if we apply a negative bias. And again, Moralt had done this where they did small deflection measurements and found increases in efficiency with that. We're just moving out, so instead of moving about 5 microns, we're going to just push it out about 100 to 150 microns and alternate the residual stress in a pressure deflection relationship. So just to give you a little cartoon, what we're going to do is if we had no charge generated, we fluctuate between the black lines. We apply a negative bias across the electrodes and fluctuate between the blue lines, and a positive will fluctuate between the red lines. And when we do that, we oscillate our voltage across, or this is about 3 microns of PZT. This is 1 micron of PZT, so that's whatever, 8 volts per micron. We get a difference between the positive and the negative. That's the red and the blue. And of course, if 1 micron of PZT is good, let's thicken it up, make 3 microns of PZT. And if we make 3 microns of PZT, we get a much larger kind of deflection difference as we oscillate. I just did this one negative. Dylan actually did this one. So that way you don't pop the membranes off when you pressurize them. and we can work out what the change in deflection is for that change in field across the electrodes. And so the work we're doing when we oscillate that field, well, we have our pressure deflection relationship here for the positively charged system. And when we switch to a negative field on it, we bump over to this line. So we're going to go out, over, back down. That lets us get a change in work. And if we know the change in work, we know the mechanical work, and we know the electrical power we put in, and so that lets us basically say that our coupling coefficient as a function of strain in the membrane should go something, or deflection should go something like deflection squared divided by the limiting k-squared value and a constant related to the pre-strain in the membrane. And what we end up with, remember I said the best we're ever going to get in this material is somewhere around 5%, 6%, somewhere around here, is, and this is actually data, not a calculation. Just Dylan takes a lot of data points and we plot them and they look small. We end up with something that actually follows a trend that has this kind of formula and lets us back out a pre-strain parameter. This material should have been maxing out for this particular thickness at about 1 micro, about 1% k-squared. So that's a factor of 2 between friends. Put on a 3 micron PZT film, that should max out at about 4 to 5%, and it goes to 2%. You can see our coupling coefficient actually increases with deflection. So in other words, we have a piezoelectric structure that we operate as a small resonating structure, has a k-squared somewhere in the neighborhood of 0.001%, which is exactly what we were measuring when we oscillated them and did the electrical analog to the mechanical test. When we start pushing them further and further, we find out that their efficiency should increase, and they should actually behave better the harder we push them. We've done this for a lot of different systems. We make 3 millimeter, 4, 5, 6, 7, 8. It's the general question we get from our funding agent is, can you get more power out of these? And the trick is make them bigger and bigger to get more power out of them. So we have somewhere around, I think 6% is about our limit right now, and they all fit the same kind of trend that they behave more efficiently as we strain them further, which works out pretty nicely for us.
So David, I'm trying to understand, so you are still talking about an oscillatory heat load in the system?
Yeah,
but
for this measurement we're doing it. So this one, since it's a piezoelectric, we could do it a couple different ways.
Okay.
This measurement is an electrical oscillation measuring the mechanical response. These measurements of individual data points are a pulsed heat and a measure of the mechanical response. So instead of putting in an electrical heat or electrical oscillation on the piezoelectric and measuring displacement, here what we're doing is we're heating a cavity, bouncing fluid out, back and forth with a small resistance heater underneath. We can do the same thing with a mechanical thermal switch that oscillates the cavity. So since it's piezoelectric, we can either put in electrical and measure the mechanical response, or put in mechanical strain and measure the electrical response. They have the same form.
And if you were scavenging waste heat, which would be, let's say, a DC heat source,
right,
you
need an oscillating heat source. So you need a thermal switch that you have to scavenge some of the electrical power off, or have a battery that starts it. So yes, that's just like we got to start a car with a battery, we need a battery to start off the heat source. For vibration harvesting, you would just use, you wouldn't worry about the fluid underneath and all that other stuff that makes life harder for us. But nonetheless, you have an oscillating heat source. As we stack devices on top of one another, then you only have to actuate the initial heat source, moving up and down. The expansion hits the one above it and transfers the heat through a thermal switch. So, so I've been, I guess, sloppy and not reminding folks what we were doing in terms of if it was electrical or mechanical, but it's because for piezoelectric it doesn't matter too much. Okay, the other thing we get off of this is, since we never generate that much power, and it has a whole host of problems with heat transfer and such, and we keep working on that, you look for other things to do. And what you find out is that the sensitivity of a device in this case is really dependent on the change in deflection divided by this first component, or change in, the first component here. I'm sorry, I missed, that's not supposed to be a C. I apologize for that. Change in deflection as opposed to the change in mechanical strain energy in the membrane. Let me jump to the next slide, which should have, no, I still did it wrong. I apologize for this. What we end up finding out is that since the thing is coupling, the better piezoelectric coupling as strain increases, you end up with a more effective sensor or actuator as you increase the strain, which is kind of counterintuitive. You usually would think that you get a larger throw if you didn't pressurize the membrane as much, but you're getting better electromechanical coupling once it's in the 3-1 mode rather than having a bending mode. So in other words, when you have a membrane, treat it like a membrane instead of like a cantilever, bulge it out, and it turns out it actually performs better at large deflections. You get a maximum sensitivity to this device.
So
yeah.
lead zircon and titanite is actually a ferroelectric, so you had to pole it.
Yeah.
So which direction did you pole it?
What do you mean, which direction?
Well,
it doesn't matter in the overall scheme of things.
Well, you could have actually done it radial.
Oh, no, these are all 3-1 modes. Okay. So if you did interdigitated electrodes to take advantage of 3-3 kind of modes, you do get different sensitivities, but they actually end up scaling the same way for membranes. For cantilevers, then you have to worry about the neutral axis, and if you had a thick piezoelectric film, if you don't make a bimorph, your results are, if you don't pull the compressive side, the tensile side, opposite, then it doesn't work. So these are all 3-1 mode, and we're going to go to large strains.
Once you bias it, of course, then you develop large radial strains as you pressurize it.
Yes, but not the radial strain is what's giving you the 3-1 mode on it.
Yeah, the shear. Yeah, it's shear in the plane.
Right. So we strain it out, and it's the same as if we just apply the biaxial strain, and we neglect bending. Anyways, the sensitivity of the device actually increases as you deflect it outward when it's working in this mode. The reason we stick to these kind of modes instead of making complex interdigitated things is this is really simple. I'm a simple person. It's an easy structure to fabricate, and if we're to stack up and make sheets of these, we need something that we can do more than 2 of, and preferably have it much easier to manufacture than if we had to interdigitate electrodes on all of them and then do each one separately. We also end up with about it's easier to do the heat transfer when we have a blanket, when we hit it. So I went relatively quickly. I tried to keep to half an hour, and I actually did a half hour. So anyways, in all cases for an engine, we have a membrane. We have an experiment that couples it to the pressure-limited case that we actually have in our engine. The way we improve the piezoelectric coupling of the membrane, minimize everything that's not piezoelectric, ignore the neutral axis, and just make more piezoelectric film with a lower residual stress and strain it as far as you can. And don't follow rules for bending cantilevers when you're working in membrane strain conditions. So, with that, thank you very much.
So is it obvious that using a phase change material would be better than just using, let's say, a bimorph material that buckles with a temperature change?
It's not necessarily obvious, but this is the heat the heat transfer that we do in and out of the cavity. Max, we can get to about 200 hertz for 15-degree delta T in and out of the cavity, and so we've done that as a relatively efficient way of generating a pressure pulse on the membrane.
Let me continue this question for a second. Okay, so you have a 5% change in absolute temperature.
Yep.
Right. So if you went to
about 3% actually.
Okay. So if I went to helium gas rather than a phase change fluid inside there, all I'd have to do is adjust the the height of the cavity so that I get also a 3% or 5% change in volume. But that then lets me span a large temperature difference between T hot and T cold rather than being tightly constrained to the phase change.
But
so the Carnot efficiency is going to go up.
Right, but the whole point of why we started this was to try to scavenge low-grade waste heat with small delta T's.
Sure, but that's still only 5% of the absolute temperature. That's a pretty low-grade
Right.
source.
Right.
So you could, I don't see why you would
No,
be
they're-
better
they're-
off with an ideal gas.
And if we had a higher delta T, that is what we would
No,
use.
what I'm saying is, the delta T that you have to put in to determine Carnot efficiency is the temperature between
Hot and cold.
in the fluid, not from your heat sinks, because it's only the active element is the phase change fluid. So as the phase change pressure changes with temperature, you get a little delta T, and that's the piece that controls the Carnot efficiency in such an engine. This is the reason that well, there's a long story there, but if you try and make a Carnot cycle in which the pressure doesn't change, the efficiency is zero, because you're dumping heat energy in.
Right.
And
Okay, yeah.
yeah. So
Right,
so
if we use this like an actuator and don't, I guess I actually lost over.
I'm not explaining this very well.
Okay.
But you need to be able to transfer. You need to have. So the Carnot cycle works as I have a hot heat exchanger and a cold heat exchanger.
Yes.
So I couple to the hot heat exchanger. Something happens. For
Yep.
example, the gas expands.
Yep.
Okay. And during that expansion, it does work.
Yep.
Then I couple to the cold heat exchanger and it contracts.
Right.
If I have an ideal gas, I can have, whatever, 5% of absolute temperature between hot and cold. But if I have a fluid that undergoes a first order phase transition, then the temperature, the real temperature between hot and cold is determined by the temperature at which the phase change occurs at the high pressure and the temperature at which the phase change occurs at the low pressure. You're completely constrained by the properties of the fluid there.
Right.
And that delta T could be very small in your device because you're only going a quarter of a bar or so in pressure. So if the difference in phase change temperature isn't roughly the difference in temperature between your heat exchangers, you're throwing away a lot of efficiency. I'll talk to you about it later.
I was going to say that I will preface something here. My background's primarily piezoelectric materials. My other collaborators are primarily thermal and heat transfer folks, so I apologize if I get things wrong on that. The other thing
These are subtle points.
There's one other thing I did forget to mention, which I should. We operate the device when it mechanically resonates, so there's a compression stroke. If we just actuate it, then all we've done is make an actuator that pops up and goes down and doesn't actually do mechanical work.
Yeah.
So this only works when we can get the system to resonate so that we end up with a compression stroke, and we time it so that we put heat in at the proper point and take it out at the proper point in the cycle. Otherwise, our PV diagram is a straight line, which doesn't actually make us anything. The PV diagram kind of ends up looking like that.
Well, that's good.
Right now. Right. So, and we end up with about 0.25% efficiency off of what should be a Carnot efficiency of 3%. So we're about 10% of Carnot with this setup.
That's an inconvenient question.
Oh, that's fine.
One of the ways to judge the efficiency of a device, especially power generator, is market. So if I ask you, what is the price of the energy it will produce during lifetime with respect to the cost that the device costs you, including the energy to produce it, the materials, your working time, everything.
I have no idea.
That's an interesting
It is an interesting question. The pitch is if you're scavenging, it'll be free eventually. You just have
nothing
to,
is free.
Yo, I know that.
There's
There ain't no such thing as a free lunch.
That's all.
Therefore,
He's got no moving parts converter that has no obvious limit to its lifetime.
No, there is limit of lifetime, of course. Everything cracks eventually. You bend it.
Right,
It will crack eventually.
we have done mechanical tests. And just to let you know, one of the membranes have lasted 3 billion cycles for the strain range we use, and that's when our testing rig broke, so we just gave it.
Something will break down.
But yes, eventually, and the gas and fluid eventually will leak out because we
Absolutely.
can't get everything sealed perfectly. Eventually, there'll be problems.
Something gotta give up.
No question.
It is lifetime
Right.
technique.
And if we could lower the cost to, if we manufacture in silicon wafers instead of roll bonded sheets of something like PVDF, the cost will still be extremely high, which means our customers will be primarily DoD rather than any potential energy generation market. Okay.
Well, thank you very much. And before everyone leaves, there's going to be an announcement by Councilor. All the speakers are coming.
So I wanted to take a moment to acknowledge our conference administrator, Rose Romero here, who's done behind the scenes, made everything work very smoothly and made sure that the hotel treated you right. And I hope they treated you right.
Outstanding job he did.
Great. And so we wanted to acknowledge